He's an undergraduate at University of the Pacific. He's a rising senior. He'll be talking to us today about some research he did last summer in Italy with Isabelle Paris, who's at the National Institute for Astrophysics in Italy. However, this summer he's in the Boston area because he's visiting CFA, doing research with Alicia Soderberg's group on supernovae type stuff. And he's here jointly with the SAO program and the Banneker Institute. I got it. So please welcome.
Thank you. If we're going to see the slides, you might need to switch.
Yeah,
which side is it?
Yeah, one of those.
Below? Yes. And then go around the other side to the blue.
There we go. Thank you.
Is there a way that this can connect to?
No, it doesn't. I tried.
Oh, so I'm
going to have to. Sorry about that.
You are here? Okay. All right, so thank you again, Leah. Dr. Krause, again, my name is Keyamo Johnson, and my project the title of my project is Transverse Flux Correlation of Quasar Pairs. I'll explain more about that later on in my presentation. But before that, I'd like to give a few acknowledgments of a few people and entities that were able to help me be here, especially Dr. Crowley for letting me come here and be able to present to you guys. So thank you. And before I get into my research, I'd like to talk a little bit about the Lyman alpha force and why that's important and how we're able to obtain that. And so this image here, I'm pretty sure a lot of you guys have already seen this image before. And in this image, I inputted a quasar here, and also the Milky Way galaxy here at present time. And so what I'm looking at is the journey of the light that's traveling through the quasar throughout the universe. And so as it's traveling throughout the universe, it's kind of with various objects throughout the universe. Some of those objects are hydrogen, which is located here, large hydrogen clouds, and also surrounding that hydrogen clouds is dark matter. And so when the quasar light gets to us, we get a lot of information about the interstellar medium and the light that the quasar light has passed through. But what I'm really focused on is the Lyman alpha force, because it tells a lot of information about the hydrogen clouds that the quasar passed through. And so here goes a spectrum of a single quasar. And so I kind of want to explain what I mean by quasar pairs. And so what I mean is quasar pairs, they're not actually interacting with each other. They're actually separate. I'm looking at the separation that they are in angular separation. So there's a certain distance. And I also want to find the transverse flux correlation function of each of those quasar pairs. And so each of those quasar give off a spectrum that we can kind of think of in an array. And so what I'm doing is I'm taking that array of the Lyman alpha force, and I'm actually correlating each element in that array. And so it's like I'm taking x1, y1, x2, y2, so on and so forth, to find a correlation and see how similar those are to each other. So that brings up a question: why am I looking at quasar pairs? Why not just focus on one quasar spectrum? Because that gives us a lot of information as well. But the reason why I focus on quasar pairs is because I really want to put constraints on these hydrogen clouds. I really want to put constraints on the sizes of these clouds. I want to see how massive they are. And the way I can do that is I have these quasars here, located as the yellow dots. And as we see, these hydrogen clouds are here in blue. And so as the light from the quasar travels throughout space, it travels through these hydrogen clouds, and it creates some type of spectrum. And so these two quasars here should have very similar spectrum because they're going through the same clouds, versus this quasar and this quasar. And so what we'll see when I do a correlation function, that these two quasar pairs here will be highly correlated, versus like this quasar and this quasar won't be so correlated. And so what I'm doing in the end results is I'm actually seeing that how massive these, or not how massive, sorry, how large these clouds are in size. And just to kind of see how these spectrums look, here goes a diagram of that. And what I'm actually looking at is the overlap between the two. And as you see here, these spectrums look pretty similar. If we just focus on this Lyman alpha emission line, but they're shifted because now all my quasars are at the same redshift distance, so they're going to be shifted by some. And so what I'm doing is taking an overlap of the Lyman alpha forces of each of these quasar spectrums, and I'm finding the correlation between those two. And so this research that I'm doing, I'm basing off previous research, Kapilani out 2006. And in this survey, they used the VLT survey, and they had about 32 quasar pairs in their survey. And this is the correlation function they got here. As we see, it has large error bars and everything in that. In my data, I'm using the Sloan Digital Sky survey, DR12, the boss part of that, and I have about 6,459 quasar pairs. 2 orders of magnitude more quasar pairs than the previous data. So that's what I plan on seeing is that my error bars or my correlation function should be much smaller, and I can put stricter constraints on cosmological parameters. And so last summer I was able to produce some results, and this was my results that I got. And so this blue dots represents each correlation output of all the 6,459 quasar pairs, and the red dots represents the bin data. And so when I first got this, I just looked at it and I see like it's just a straight line, and I thought that this wasn't telling me too much information. And so if I take away these blue dots and just look at the red dots, I can actually see the correlation function in a finer scale. And what this is telling me, what I get from this is as we get farther and further angular separated, we get less correlated, which is expected in this in the correlation function. But what I found actually recently, like last night actually, by plotting this data on top of but plotting this data on top of the Kapilani et al. Data is that they share a similar shape. As we see, my data is shifted up by some distance, and I think that's due to the fact that we use different normalization parameters on our spectrum, so that's maybe the reason why. But what I really want to focus on is the shape of my correlation function. And so this is the 32 quasar pairs from Kapilani et al., and this is my bin data here. And if you can kind of like look or squint, I guess, you can see that it follows the same shape within the correlation function. And so not only am I using 6,459 or 2 orders of magnitude more quasar than the previous study, but I'm also using another survey, and I'm still getting the same results or similar results that they showed in 2006. And so what I'm assuming is that this is something that's physical in nature that produces this correlation function. And so as I said, I got these results last night, so it's still a work in progress. I'm still trying to figure out what are the analysis, what are the results that I can get from this. One big thing that I really need to do that Dr. Tellis told me I need to do is put error bars on the results to see actually how fine I will be able to put constraints on the cosmological parameters. I need to understand the normalization discrepancies between the two. I also want to investigate the shape of the transverse correlation function. Like why is it actually that shape? Why does it look so similar to the Kapilani et al.? And then also I wanted to try different correlation functions as well. I only talked about one in this project, transverse flux correlation, but there are also other ones called longitudinal correlation function. But then my end result was what I really want to do is put strict constraints on these cosmological parameters such as dark matter, dark energy, and stuff like that by plotting, making computer simulations of a universe and finding a correlation of those quasars in that universe and then plotting it against my function. And so that's the end of my project. Thank you for letting me be here. Any questions or ideas of what I should be doing next? Thank you.